So let's start. It is a pleasure to introduce Bruno Klingler from Humboldt Universität in Berlin. And he'll be speaking about the Zilber-Pink conjecture. Bruno, thank you very much.
Yeah, thank you. So first of all, I would like to thank the organizers for inviting me to speak here. I'm very sorry. I'm also apologizing. I was supposed to be in person in Miami, but 2 days ago I had to cancel my flight for serious family reasons. So I apologize for that. I know that Zoom talks are not great. Personally, I hate them, but well, I would try to do something. And also, exactly for the same reason, I was planning to give the talk on the board, so I didn't have time to prepare typed slides. But I hope my slides will be readable. Please interrupt me with any question if there are any. All right, so I want to talk about the Zilber-Pink conjecture. So what is it about? Well, let's give some motivation first. So the motivation is the following situation. You start with a family, let's say, of smooth proper varieties of a field K. And you would like to understand the complexity of the fibers of this morphism, F. And in other words, for using big words, let's say you want to describe the motivic locus. By this, I mean you want to describe a set of points in S such that the fiber is in some sense simpler than the very general fiber. So what does it mean, simpler? Well, this means that the motive of this fiber should be simpler than the very general one. So you can ask this question using different incarnations of motifs. For me today, everything will be of a C. And so basically, the incarnation I will be considering will be Hodge theory. So to such a family F, I will associate a variation of Hodge structures. In this setting, this is a pure variation. This means that, first of all, I have a local system of finite rank Z modules, Ri F lower star Z, where I fixed some integer I. So this is just the local system of the topological cohomology of the fibers. And well, there is a Durham incarnation of this local system. Namely, you can look at algebraic vector bundle, which is this I F lower star of the relative Durham complex, endowed with its Gauss-Manin connection nabla, and F is the Hodge filtration on this algebraic vector bundle. And of course, if you take the identification of this algebraic vector bundle, then it corresponds to RIF lower star Z, let's say C, by the Riemann-Hilbert correspondence. And then in the background, and I will not insist on that here, there is a polarization form on this cohomology that I denote by Q, and which will play a crucial role, although I don't want to emphasize it here. Okay, so this is the general motivation, and now basically we want to understand the points where this variation of a structure, the fibers of this variation of structures are simpler than the very general one. Actually, we will work purely in Hodge theory. In some sense, we want to forget, at least for now, that things come from geometry. So we can consider any admissible graded polarizable variation of mixed Hodge structures. So this means that you have, rather than having a family of pure Hodge structures coming from such a morphism, you have just a family of mixed Hodge structures satisfying a lot of conditions, mimicking what happens in the geometric situation. Okay, and then in this setting, the motivic locus becomes what is called the Hodge locus. And what is it? Well, this is a set of points in the complex manifold S analytified, such that the fiber Vs of this variation has exceptional Hodge tensors. And by exceptional, I mean that those Hodge tensors appear at that point S, but they do not live in the very general fiber around S. Okay, so is this setting clear, or are there any questions? All right, so now let me maybe give examples because not everybody is necessarily familiar with this kind of questions. So a typical example will be you look at the universal principally polarized abelian variety. So AG, a curved AG is a moduli space of such principally polarized abelian variety, and the morphism is just the universal abelian variety. Of course, you have to put some level structure, but let's forget this. So in this situation, the Hodge locus will be a subset of this curved AG. And this subset, if you try to describe it, it's pretty complicated. But at least let me give you some feeling of what you can get. So on the one hand, for instance, you can get some objects which are of geometric significance. You would get all the points in AG such that the corresponding abelian variety AS splits as a non-trivial product. So this is the geometric AG case that I've written on the right. So AS, at that point, AS is AK cross AG minus K, where AK is a K-dimensional abelian variety, where K is between 1 and G minus 1. And you split your abelian varieties this way. Such a splitting, of course, induces Hodge class, which is a projecture of the Hodge structure corresponding to the splitting. Another kind of things that you can get are just points, namely abelian varieties admitting complex multiplication. So those ones are much more arithmetic in nature. So you see that if you try to make a picture of this Hodge locus in the moduli space of abelian varieties, then actually you would get a countable union of what is called special subvarieties, so countable union of irreducible subvarieties, which are all defined of a Q bar and which happen to be analytically dense in AG. And all this is completely non-trivial. The point is that this is the theory of Shimura varieties that tells you that already the CM points are analytically dense in AG, right? But the positive dimensional subvarieties, special subvarieties, are also analytically dense. As I said, if you try to really describe this locus purely in terms of abelian variety, this is pretty complicated. But hopefully for us, all this was done in great generality using only algebraic groups, first by Shimura, and then, of course, developed by Deligne and the formalism of Shimura data. So any questions about this example?
I don't understand what is being considered. How are you getting these special subvarieties?
Yeah, so what I'm saying is that this Hodge locus, it happens in this case just to be a countable union of algebraic subvarieties. So if I look at the locus where exceptional Hodge classes appear in the fibers of Mar variation, so here the fibers are just H1 of the corresponding abelian varieties, and then you look at Hodge tensors appearing in this Hodge structure, okay? And what I'm saying is that actually you can describe it purely in group theoretic way. And as a result, at the end of the day, is that this Hodge locus, which was defined purely set theoretically, happens to be a countable union of irreducible subvarieties that I will call the special subvarieties. Moreover, as is well known, AG is defined of a Q, and those special subvarieties are all defined of a Q bar. And the third part of the result is that this union is in fact analytically dense in AG. Does it answer your question? As I said, I cannot do much better to describe explicitly, completely what is this Hodge locus in this situation. This would be too complicated in terms of just of abelian varieties.
Second question. What do you mean by Hodge classes?
A Hodge class, sorry. So maybe I should have made some prerequisite here when I was looking at a Hodge at Hodge theory. So a Hodge structure, basically Hodge structure H will be something a Q vector space of finite dimensions, such that when I complexify it, you get a direct sum of HPQ, where HPQ bar is HQP. Okay, so this is our structure. And now Hodge class in this Hodge structure is something, a lambda, which is in H00 intersected with HQ. Okay, But now I'm not only looking at Hodge classes in the corresponding Hodge structures, I'm really taking Hodge classes in the entire tensor algebra. So I take H tensor A, tensor H tensor H dual tensor B. Sorry. And I look at this big thing, and a Hodge tensor is Hodge class in this infinite dimensional Hodge structure. Does it make sense?
These are the classes that are supposed to be related to algebraic subvarieties.
Sorry?
This is related to the Hodge conjecture.
Okay, so I will come to that. So, but you are perfectly right. The fact that you realize in that case that this is a countable union of special subvarieties is predicted by the Hodge conjecture. But I will come to that in one moment. Okay. More questions? All right, so let's give maybe a second example, and this second example is actually related to Lefschetz. So rather than looking at the universal principally polarized abelian variety, let's take the universal smooth hypersurface of degree D in Pn+1. Another very natural object, maybe even more natural than the previous one for a classical algebraic geometer. So this means that I am looking at the parameter space UND of smooth hypersurfaces of degree D in Pn+1. So I just take H0 of Pn+1 OD, I projectivize, I remove the discriminant locus, which is hypersurface, and I get my UND. And then over UND, at each point, I have a hypersurface of degree D in Pn+1, and the union of those hypersurfaces is X and D. Okay? So for n is equal to 2, so this means that I'm looking at surfaces in P3 of degree D, and let's take D at least 4, then this is a very classical story. So now I'm looking at the Hodge locus in U2D for this variation of a structure, which is looking at the cohomogene degree 2 of the surface. And I'm asking, when do I have exceptional Hodge tensors for this Hodge structure? Then obviously in this Hodge locus, I have what is called the Noether-Lefschetz locus, NLD, which correspond to the set of surfaces Z such that their pK is not Z. So a very general surface of degree D in P3 for D at least 4, I mean, the pK will be just the pK of the ambient projective space, but there are a few surfaces such that the pK is actually bigger, okay? And then where Lefschetz play a role was in 1920, he proved that this was, there was a first indication by Noether, but the proof was not complete, that this Noether-Lefschetz locus is actually already a countable union of irreducible subvarieties that I call special subvarieties again. Okay? So this was a contribution of Lefschetz. And then much later, Green and Voisin, they proved they were able to actually bound the codimension of any special subvariety in this Noether-Lefschetz locus. So the generic case is when the codimension is H20 of the surface, right? I mean, if you want to have an exceptional class, you have to impose the vanishing of H20 parameters. And so the generic special subvariety will have codimension H20, which can be computed easily. This is just D-1 choose 3. Okay. And but they also prove a lower bound, namely you have bigger dimensional components, which where the codimension can be D-3. Okay. And this corresponds to the family of surfaces in P3 which contain a line, a P1. This is also a part of the result. Okay. So you see already that in this quite simple situation, the description of the Hodge locus is pretty complicated, even if I restrict myself only to this Noether-Lefschetz locus. So Green and Voisin gave the following definition. A special subvariety Y in the Noether-Lefschetz locus is called general if it has the expected codimension H20 and it will be called exceptional otherwise. Okay, if it has a dimension bigger than expected by intersection theory. Then in 88, Chiliberto, Harris, and Miranda, and then Green proved that actually the union of those special subvarieties, which are general in the previous sense, so the ones which should be the most common, this union is actually dense in U2D. So the first three authors proved it for the Zariski topology, and then Green proved it for the analytic topology. So this is actually analytic dense in U2D. So this is what happens for the special subvariety which have the expected dimension. And then Harris conjectured that there are only finitely many exceptional ones, namely the ones with bigger dimensions than expected. Okay? But Voisin disproved this result in 91. And then she has the question whether if you take the union of all the exceptional ones, is it Zariski dense in U2D or not at all? Okay. Then you can go in higher dimension. So now we are working with hypersurfaces in Pn+1, where n is strictly larger than 2. And then, well, basically nothing was known about the Hodge locus before the next result, which occurred in 95. So I hope that those two examples help you to get some feeling about what this Hodge locus is. In those two cases, you see that the Hodge locus is a countable union of algebraic subvarieties, actually all defined over Q bar in our situation, and that they are analytically dense in the space we are considering. Okay, so to come back to the previous question, let's go back to a general morphism, X to S. And then Vail, in his last paper, noticed that actually the Hodge conjecture implies that this Hodge locus for geometric variation is a countable union of closed irreducible subvarieties of S. And those irreducible subvarieties, I would call them the special subvarieties of S for this variation of Hodge structure. And the reason is pretty simple. Each time you have a Hodge tensors appearing in a geometric family, in a geometric variation, according to the Hodge conjecture, it should correspond to the appearance of an exceptional algebraic cycle, maybe not directly in the fiber of F, but in some product of them. Now, the point is that algebraic cycles have the nice properties that you can glue them together using the existence of Hilbert schemes. And so this means that when there is one appearing, they will appear in algebraic families. And so they will project onto an algebraic locus in the base. And this is basically the argument of Vail. Okay. What happened is that in 95, Katanidolin and Kaplan actually proved unconditionally for pure variations of structures, not necessarily coming from geometry, that this is true. Namely that in full generality, the Hodge locus is a countable union of closed irreducible algebraic subvarieties of S. And this was generalized to the mixed case by Brosnan, Perlstein, and Schnell. And there was a different proof by Kato, Nakayama, and Usui. And so also some work by Ben Baker, myself, and Jacob Zimmerman. Okay, so in 95, you can say that on total, what we know is whatever the kind of variation of mixed structure I'm considering on S, all of them are, in this talk, are always graded, polarizable, and admissible. This is technical conditions. Then the Hodge locus is this countable union of closed irreducible algebraic subvarieties of S that I would call the special subvarieties for the variation. This is pretty remarkable, right? I mean, each time you start with such a variation, you get for free a countable union of algebraic subvarieties. And now the big question, and this is what the Zilber-Pink conjecture is about, is what is the distribution of those special subvarieties? So we have seen in the two examples that I told you about that those special subvarieties are actually, they were actually analytically dense in the moduli space we are considering. And the question is that always the case or not? Okay, so let's now present the conjecture. The conjecture before presenting the conjecture, maybe I will explain the first result, which goes in an opposite direction. So the first theorem obtained by Greg Baldi, myself, and Emmanuel Ullmo in 2 years ago, published 2 years ago, is that actually, if we look at the Hodge locus for this universal family of hypersurfaces in Pn plus 1 of degree at least 5, and I'm assuming that ND is not 4, 5, then the situation is completely different from what happened for families of abelian varieties or of surfaces in P3, at least if I restrict myself to the union of special subvarieties of positive period dimension. So basically, you have to think that this Hodge locus, this is a countable union of algebraic subvarieties. I can discard the ones which are points. I keep only the positive dimension ones. And then in this situation, what we prove is that actually the Hodge locus of positive dimension is algebraic. So it does not mean that you have only finitely many special subvarieties, but it means that you have only finitely many maximal ones of positive period dimension. All the components of the Hodge locus of positive dimension, they are contained in finitely many maximal components. Okay. So this is completely different of what happens for families of abelian varieties or for surfaces. And we also answered more recently the question of Claire, which is that if you go back to the case n is equal to 2 and d at least 5, and if you look only at the exceptional components of this Noether-Lefschetz locus, so the ones which are not of the expected dimension, then their union is not Zariski dense. So the exceptional components, although you have usually infinitely many, they are not Zariski dense. The Zariski closure is strict inside U to D. All right. So what is the heuristic guiding you to this kind of conclusion? Well, this is exactly what the general Zilber-Pink conjecture is about. So let me try to explain now a bit how you can get an intuition about this kind of result. So to do so, we'll go into just usual period map theory. So the claim is that you can forget about this kind of linear algebra data given by a variation of mixed structure. So this local system and this bundle with connection and filtration. And just keep in mind that this is essentially the same thing as giving yourself a period map. So what is a period map? This is a complex analytic map. It is not algebraic at all. Going from your base, well, the complex manifold associated to your base, so Sn, to some period domain d mod gamma. So I have to explain a little bit how it works. So if you have a mixed structure V, then you can associate to it an algebraic group of a Q, which is called its Mumford-Tate group. And what is this Mumford-Tate group? Well, this is the subgroup of GLV, which stabilizes all Hodge tensors corresponding to V. Okay, in all tensor powers of V, tensor is dual. Okay, so this group completely controls the Hodge structure V. And so now if you have a variation, you can think of this variation as being a family of algebraic group over your base. And it happens that this family, by a result of Deligne, is a locally constant sheaf of groups exactly outside of the Hodge locus where the group drops. Okay, so outside of the Hodge locus, you have a generic Mumford-Tate group, G, and on the Hodge locus, at each point, then the Mumford-Tate group becomes smaller because you have more algebraic, you have more Hodge tensors. All right, so now what is this period map? Well, basically you try to classify those Mumford-Tate groups to each point of S. You will associate the corresponding Mumford-Tate group, and D is basically a parameter space of all possible Mumford-Tate subgroups of a given group. Okay. And gamma is G of Z. So maybe I should have said that, but in the case of AG, well, it's well known that AG is exactly one of those period space D mod gamma, where D and the generic Mumford-Tate group is just sp2G of a Q. Right, to give you an idea of what those spaces are. So in this very special situation of AG, you see that actually AG is an algebraic variety. But in general, D mod gamma is far from being an algebraic variety. So let me explain a bit the geometry of D mod gamma so that we can understand what the Zilber-Pink conjecture is about. So the thing is that because D is classifying essentially Hodge structures, when I look at the tangent space of D mod gamma, it is endowed naturally with a filtration by a holomorphic subbundle. So the Hodge filtration induces a Hodge filtration on the tangent bundle to the moduli space of Hodge structures. And let me call this Hodge filtration F. And so the deeper part of the filtration is F minus 1, and then it goes to a certain F minus L, which is a full space, which depends, of course, on which Mumford-Tate group you are considering. Now, a basic fact about period maps is that there is a very strong requirement about them, which is that the differential of phi has to map the tangent space to S to the deepest part of the Hodge filtration. So you have a very strong system of PDEs which have to be satisfied by phi because it has to be tangent to this F minus 1t. Okay. The second remark is that a basic invariant of the situation is the depth of this filtration, what I call the level rather of V. And this is this L appearing, which is the number of steps in the filtration that you have. And the basic idea is that due to Griffith's transversality, the bigger L, the stronger the constraint of being in F minus 1 is, right? If I take a random map inside D mod gamma, it has very little chance to be in F minus 1, except L is equal to 1. And now the basic fact is that this case corresponds exactly to the case where D mod gamma is in fact algebraic. And in that case, D mod gamma is exactly a mixed Shimura variety, essentially. And you can prove that the period map is algebraic. But you see that this is very rare in the world of Hodge theory. So Hodge theory is essentially non-algebraic. And there is some exceptions that correspond to moduli spaces of abelian varieties and maybe a little bit more, like or one motifs, like these mixed Shimura varieties. Now, to say that the picture is complete, you have also to describe the Hodge locus in terms of these period maps. Well, this is very easy. If you have your period domain D mod gamma, you are looking at points where the Mumford-Tate groups become smaller. But the points where the Mumford-Tate groups become smaller, this is a countable union of analytic subvarieties of D mod gamma of the form D prime mod gamma prime, where G prime D prime is a sub-Hodge datum of GD, right? So everything on the right is analytic. And then the Hodge locus of your variation, this will just be exactly the pre-image of all those D prime mod gamma prime. So here I should put a strict. Okay. Any questions about this picture, which is a very classical picture about period maps? Right, so this means that you have the following picture. If you want to describe what is special subvarieties, well, you have this D mod gamma, which is a locally homogeneous space, complex analytic. Inside D mod gamma, you have a lot of guys of the form D prime mod gamma prime. And then Y in S will be a special subvariety if it is the pre-image under the period map of such a d prime mod gamma prime. So I try to make a picture. In green, you have this phi of y, which has to be the intersection of phi of Sn with some pure domain d1 mod gamma subdomain dy mod gamma y inside d mod gamma, right? So this means that you can interpret those special subvarieties as being complex analytic intersection loci. Okay, and what is remarkable in this Catani-Dellin-Kaplan theorem is that although the map phi is analytic and dy mod gamma y is analytic, this preimage, the irreducible component of the preimage, analytic irreducible component of the preimage, is actually algebraic and not only analytic. Okay, but now once you do intersection theory, even in the complex analytic setting, you can decide whether this intersection is atypical or not. So by atypical, I mean that it does not have the expected dimension. In other words, I would say that a special subvariety is atypical if its codimension inside the image phi of S is strictly smaller than its expected codimension. That should be the codimension of dy mod gamma y inside d mod gamma. Okay, so those atypical ones, they should be kind of rare, while the typical ones, where you have the expected dimension, should be much more common. And now you can remember a little bit what happened in the case of the Nutter-Lefschetz locus, those exceptional and general components, and exceptional in that setting would be atypical, and general would be typical. All right, so now what is the Zilber-Pink conjecture for variation of mixed structure? So this is a conjecture I made in 2016, and in a more restricted way, and then we generalized it with Greg and Emmanuel in 21. It tells you that just that if you take any variation of mixed structure on an irreducible algebraic variety S, then S contains only finitely many maximal special atypical subvarieties for V. Okay, so the guys that should be rare should be rare. It's very difficult to have an atypical. It should be difficult to have an atypical intersection. Okay. So let's look at this conjecture and let's give special cases of these examples of this conjecture. So the first special case is the classical Zilber-Pink conjecture that was conjectured independently by Pink and Zilber in the 90s for Shimura varieties. They were considering only pure Shimura varieties at the beginning, but you can do it for mixed ones. And in this situation, so remember that the Shimura variety is exactly one of those D mod gamma, which is algebraic. And the period map is algebraic, so you can reduce everything to algebraic subvarieties of your Shimura variety. And then the statement is that if you take any algebraic subvariety S of my mixed Shimura variety curved S, then S contains only finitely many maximal atypical intersection with the special subvariety of the Shimura variety. Okay, so for instance, if you are inside AG and you take an irreducible subvariety and you try to intersect with all the special subvarieties that I described at the beginning, then you should have only finitely many maximal atypical intersections. Another special case is the Andrew conjecture for variation of mixed structures. Suppose you have a variation of mixed structure on an algebraic variety S, and let's assume that S contains a Zariski dense set of CM points. So now in this situation, CM points just means that the Mumford group at that point is a torus, so the smallest possible, so the maximal number of Hodge classes appearing. Well, the claim is that the variation has to be of Shimura type. In other words, the D mod gamma is a Shimura variety. The period map, which is now algebraic, should be dominant. Okay. So this is a typical kind of, and of course, if you restrict this conjecture now to the setting where actually you start with a subvariety of a Shimura variety, then you recover the classical André-Hort conjecture, which has been proven now by many people and finished by Jacob Zimmerman. All right, so let me maybe particularize this to a very simple example where we don't know the answer of this Zilber-Pink conjecture for mixed variation of a structure. In that case, I would just take a pure one. So take the simplest example, take S being P1 minus 3 points, okay? And then on S, you can easily construct a variation of weight 3 Hodge structures such that H30 and H21 are equal to 1. So you have a variation. The local system has rank 4. So for instance, you can take, you can start with a dual mirror-quantic family, right? So you start with your preferred Calabi-Yau with H30 is equal to H1 is equal to 1, and you take the universal family, universal deformation of that Calabi-Yau. You will get a curve, which will be P1 minus a certain number of points. In my case, I choose P1 minus 0, 1 infinity. And so this means that you will get a period map from that curve, seen as a complex Riemann surface, to this period domain. So in that particular case, it's easy to see that the period domain is SP4R. So this is your generic Monforte group. D is SP4R modulo U1 cross U1. So this is not a Hermitian symmetric space. It's really a period domain. And SP4Z. So on the right, you have a complex manifold of dimension 4. You have this curve there, but this period map has to be horizontal. And then if you try to interpret the conjecture that I wrote before, then in particular, you will get the following predictions that this curve S should contain only finitely many CM points. So there should be in this family only finitely many Calabi-Yaus whose Monforte group is a torus. And actually, when I made this conjecture, I was pretty happy to see that this was already conjectured by physicists, namely in this case by Gukov and Vafa, for completely different reasons coming from some conformal field theory. And you can also predict that there should be also only finitely many points where this Calabi-Yau Hodge structure becomes reducible. And actually, it was the topic of Johannes de Jong thesis, which is still not finished today. All right, so now let me move to some results. So I will start with the older results. So actually, the result that I mentioned for the universal family of hypersurface of degree D in Pen plus 1, this is a corollary of the following results. So first of all, we have a result that proves, in some sense, this Zilber-Pink conjecture in the geometric setting. So let me state the simplest case. Suppose that V is pure and that the generic Monforte group, when you take, so this is a reductive group because V is pure. I take it a joint group. This is a semi-simple group. Let's suppose there are no product troubles. So this group is simple. Like, for instance, in the case of AG. Then we prove that if we look at this union of atypical spatial subvarieties, and I look only at the ones which are of positive period dimension, meaning that their image under the period map is not a point, then we prove in these generalities that it is algebraic. In other words, S contains only finitely many spatial atypical subvarieties of positive period dimension. Okay, so this is a very general statement, at least under the assumption that the joint group, the joint generic Monforte group is simple. And actually, the right way of seeing it is we do not argue directly on Hodge structures. It's a statement purely on the monodromy of the underlying local system. So what we proved, and this was in the pure case, and it was generalized by Baldi and Ullmo for mixed variation of Hodge structures, is that if you try to parameterize the families, the subvarieties of S where rather than looking at the Mumford group dropping, you just ask that the generic monodromy of the local system on the subvariety drops, then they are contained in only finitely many families. So there are only finitely many families of subvarieties of S. So such families will be parameterized by a map Fi from Zi to Yi, and now I want the fibers to be immersed subvarieties of S. So I give myself pi I from Zi to S, which is an immersion in restriction to the fibers of Fi. There will be only finitely many families containing all the maximal monodromy atypical subvarieties. Okay. So of course, I won't have time to say anything about the proof. The proof is pretty interesting. It uses essentially two ingredients. One is functional transcendence results for period maps, which is called actionuel, that I will not describe. And the other ingredient is to say that although the map phi is not algebraic, from a topological point of view, it's pretty tame. And the right setting is to say that it is definable in some ominimal structure. And using those two things, what you do is that you parameterize the families of maximal monodromy atypical subvarieties by a set that has two properties. First of all, it is definable in some ominimal structure, which is called Rnexp. And second, it is countable. And then a basic property of definable sets in ominimal structures is that anything countable is finite. And so this is the way you prove that you have only finitely many families. So you see that what is interesting here is that in some sense there is a purely algebraic result, this functional transcendence result, actionuel, and there is the auxiliary help of ominimal geometry that tells you that also we are leaving the algebraic world. We are living. We are really using complex analytic maps. Those complex analytic maps that we are considering, those period maps, they are close enough to be algebraic, at least if we think of their topological properties. All right, so this was the main result towards the Zilber-Pink conjecture in the geometric setting, meaning that I'm not considering atypical points. Then, with Baldi and Ullmo, in the pure case, what we prove, and this was very surprising to me at the time, is that if the level of the variation, so I remind you that the level is the depth of the filtration on the period domain. If the level is at least 3, which is, of course, generic when you look at families of varieties, as soon as I'm not considering families of abelian varieties or things of level 2, what we prove is that actually the full Hodge locus is completely atypical. So in some sense, it explains completely the difference between what happens for families of algebraic varieties and families of hypersurfaces in Pn+1 for n at least 4. Right? And you can see this result as being really, at the end of the day, it's just an incarnation of Griffith's transversality. It tells you that if the level becomes too big, and big is just 3, then actually, if you want to be in the deepest part of the Hodge filtration on the tangent bundle of D mod gamma, then this is a highly atypical condition. There is no chance that you can be typical. All right, so although this is not directly related to the Zilber-Pink conjecture, let me mention this result about the typical locus. So suppose that the typical locus is different from the empty set. Sorry, it should be an empty, not a 0. So already by the previous theorem, this means that the level has to be 1 or 2. Then what you prove is that the typical the Hodge locus in that situation, where the typical one is not empty, it is analytically dense. So and this completely explains all the dichotomies that we have seen before. Either you have some typical components, but then the Hodge locus is dense analytically, or you are in the case where the level is at least 3, and then in that case everything is atypical. And if you are under the assumption that the adjoint Mumford group is simple, then actually the Hodge locus is algebraic. And then, so this is what we prove with Baldi and Ullmo, and it was refined by Khalifa and Urbanik for telling you that actually this typical Hodge locus is non-empty as soon as it has to be for numerical reasons. In other words, if there exists a d prime mod gamma prime in d mod gamma, such that the dimension of the image of S under the period map plus the dimension of d prime is at least the dimension of d, so numerically this means that there should be some typical intersection, then actually the Hodge locus is analytically dense. But of course, this condition can happen only if the level is 1 or 2. So it has some interesting corollary. For instance, if you take, even in the simplest case of families of Euclidean varieties, suppose you are in AG, and suppose that you take, for instance, for S, you can take the Torelli locus. And take any S which has dimension at least G, then actually the Hodge locus in S, so the intersection of S with all the special subvarieties of AG has to be dense, which was completely not known before those results. All right, so it's time to turn to the remaining important questions. After all these results, you see that in some sense, when you look at the Hodge locus, you are not interested anymore in the positive dimensional components because more or less we understand everything about them. So what we would like to understand now are the special subvariety of 0 period dimension, so the atypical points, if you want. So and now this is more recent work. So what we prove with Tayou is the following result. So suppose first in the Shimura case, so suppose you take a mixed Shimura variety. So this is a general fact in the theory of Shimura varieties that a mixed Shimura variety is defined over Q bar. And now you take X inside this Shimura variety, a Hodge generic. So the generic Manforte group on X is the same as the one on S. And you take this X closed irreducible. Now what you can do is you can look at the projection of X on any Shimura variety which is a quotient of S. And now you look at all those quotients which are not reduced to a point, so non-trivial. And the requirement is that those projections are not defined over Q bar inside S prime, inside this Shimura variety, which is a quotient. Then the claim is that the full Zilber-Pink conjecture holds true for X. So now this is not anymore a result on positive dimensional subvarieties, but really on even on points. So the simplest example is basically the pure case. So take a pure Shimura variety S, for instance, you can take AG, but you can take things more complicated. And suppose that, again, the generic Manforte group is simple, and that X is Hodge generic inside S. And the claim is then just that if X is not defined over Q bar, then the full Zilber-Pink conjecture holds true for X. So basically what we have done is that we have reduced the general Zilber-Pink conjecture to Zilber-Pink conjecture for varieties defined over Q bar. Okay. So once you see that, you can guess that maybe this is not so deep. It should be some kind of spreading argument, and indeed it is. But what is pretty interesting is that I thought at some point when I realized that this should be feasible, I thought it would be completely trivial and even maybe not interesting to write the details. But actually it is not, and the geometry is pretty funny. So I should mention that the result for AG was also obtained by Barrow, Hero, and Dill recently. Here we prove it for any mixed Shimura variety. All right, so time is passing fast. So let me go to the last result I want to mention today. So let's try to generalize this result with Tayou to a geometric setting. So of course, as I said, this is a spreading out argument. So if you want to spread out, you need to be in some kind of geometric situation, either Shimura case or non-Shimura case. If you are in the non-Shimura case, you want the variation of Hodge structure to be geometric in some sense. So what does it mean that a variation of Hodge structure is geometric? This means that after maybe replacing the base by a Zariski dense open subset, there exists a family, an algebraic family G Z to S, such that V is a subquotient of the variation of mixed Hodge structure given by Ri G lowest star Z. So you see here that I'm not careful at all about describing what kind of algebraic properties I want on G. I just want that when I push forward, I push forward Ri G lowest star Z, I just want this to be a D module, well, a Hodge module on S, which generically is a variation of mixed Hodge structure. Okay. And then I reduce to that open where this is a variation of mixed Hodge structure. And I say that something is geometric if it is a subquotient of such a guy. And I would say that the P-N map is geometric if it is the P-N map of some geometric ZVHS. Now, the crucial assumption is, the crucial notion is the following one. I will also say that the variation of Hodge structure is absolute if I look at any algebraic closed field of definition of this variation. By field of definition, I mean the field of definition of the variety S plus of the Durham incarnation of the variation of the mixed Hodge structure. So the algebraic vector bundle, the flat connection, and the filtration. So typically what I want to do, if I want to do some spreading, I want to take the algebraic closure of finitely generated subfield of C. Okay, so this is the kind of case that I want to consider. And then I say that the variation is absolute if when I'm defined over K, then the special subvarieties of S are also defined over K. So it is expected that any geometric variation is absolute in that sense. This is a consequence of the Hodge conjecture, or if you want, this is even a consequence of the fact that Hodge classes are absolute Hodge classes. But then the theorem in progress with Salim is the following. So suppose, and this is of course a very strong assumption, that all the variation of mixed Hodge structure of geometric origin are absolute. There are some results in that direction, but again, the problem are the points, the special points. Then I take a variation of mixed Hodge structure of geometric origin with such a P-N map, and the requirement to get the conclusion that the Zilber-Pink conjecture holds for V is that it's very similar to what happens in the case of Shimura variety. I am asking that each time I project D mod gamma to another P domain D prime mod gamma prime, then if I look at the composite, sorry, this is a big phi. At the composite of phi with that projection, I'm asking that it does not factor through an algebraic variety defined over Q bar. Okay. So again, we reduce the Zilber-Pink conjecture from the general case to the case of varieties defined over Q bar. And again, this kind of nice spreading out argument, which is not completely trivial and pretty nice to be written down. Okay, well, thanks a lot. I think I will stop here for now.